In this video, we are going to finish section 2.5, the intersections of lines and planes, which means that we are going to finish chapter 2 about lines and planes in R3, and we're going to do the problem that you see on your screen here, which is part 2 of the example that we started in the previous video, example 2.5.3, about finding the line of intersection, of these two planes. So method 2 that we're asked to do here is an algebraic method. The previous method was more of a geometric method in the previous video. So we are going to do this algebraic method to find the line of intersection of these two planes. And that's the method that you will sort of expand upon in the next section, the next chapter on linear systems. So let's go ahead and start then this method 2 by following the steps that are given to us here. And step number 1 says use elimination to reduce the number of variables. So elimination is the process of adding or subtracting multiples of equations from each other with the goal usually of getting rid of one variable. So I'm recopying the system here, and the way those equations are, I can take advantage of the opposite signs in the z and just add those two equations together to get rid of z. So I'm going to get 2x plus 2y is equal to 3. And I mean, that's the result of that elimination step, but I could go a little bit further if I wanted to, and actually I know that I will want to for what's coming next. So I'm going to divide both of those sides by 2, and then I'm going to solve for y. So y is 3/2 minus x. Now the next step, step 2, says to let one variable be free, and that's probably something that's new to you. I'll explain that in a moment, and represent its value by a parameter t. So I'm going to do that, which is usually part of the solution that you just do without explanation, but then I'm going to explain to you what's actually going on behind this step. So the way that I've set things up here, it makes sense to let x be a free variable, and that means that I want to let x be represented by a parameter t for any t in R. And that means that since we've solved for y in terms of x, y is 3/2 minus t. Now, what's really going on there? Before we go to the next step, let me explain. What a free variable is. Explanation, I don't think there's an I. Explanation of what's going on here. We've done elimination, but it hasn't given us a full solution. It's only given us this, right? And there are many, many points that satisfy this. And in fact, what we really want to do is we want to find all points that satisfy. We want to find all points that satisfy y is equal to 3/2 minus x. And if we were going about this a bit naively, we might do what we've done in previous situations. We might choose a value for one and then solve for the remaining, right? We've done that when we were picking points in a plane and that sort of thing. So let's proceed with that kind of procedure in mind. If we let x equal 0, well, if x is equal to 0, y is then determined. Y has to be 3/2. Now, obviously, that's not the only possibility. We could let x be 1/2. And if x is fixed at 1/2, y is also determined. Y is 3/2 minus 1/2, which is 1. And, right, there's more. We could keep on going here. Let x equal minus 1/2, which means that y is 2. And we could keep on doing this forever, right? This idea of choosing a value for x and then calculating what y has to be in terms of that, Well, that's exactly what is going on behind the free variable, right? Instead of saying, well, let's let x equals 0, let's let x equals 1/2, let's let x equals minus 1/2, let's let x equal t. So t represents all of our choices, right? T represents any possible choice, any choice that you could choose. And once you've made that choice, then y is determined in consequence, right? So in this case, we would be saying this is like we had chosen t equals 0. This is t equals 1/2. This is t equals minus 1/2, and so on and so forth. So a free variable is a variable that one can choose the value of, and one represents the choice of that by a parameter t. And that's why we say that t can be any value in R, right? So any value that you choose for t, you can then calculate in consequent what the value of y has to be. Now that's only two of our variables, right? We got rid of z, so let's go into the third step here, which is to use substitution to rewrite all of the variables in terms of the constants and the parameter t. So let's go back into one of the plane equations. It does not matter which one. I'm going to choose pi 1's equation. And if I solve for z, z is going to be x plus y minus 2. Now this tells me to rewrite all variables in terms of constants and t. So I'm going to substitute in what we have up here. I know that x is t, and y is 3/2 minus t, and then we have minus 2. And so I can simplify. Those t's are going to cancel out, and then I'm going to end up with z is minus 1/2. Now a solution writes down the answer for all variables, right? X, y, and z equal, well, in terms of t, we have x is t, y is 3/2 minus t, and z is minus 1/2 for any value of t in R. Now, take a look at that for a second. That looks like something. That looks like something that we've seen before. It looks exactly like the parametric equations for a line, for our line of intersection L. So if we go and write this, if we wanted to in vector form, that's x, y, z is equal to 0, 3/2 minus 1/2 plus t times the vector 1, minus 1, 0 for t in R. And if you go and check what we did at the end of the last video, that was the answer that we got from our geometric method as well. So this is an algebraic approach using free variables to find the line of intersection of two planes. Here's my final answer using this algebraic method. And I just want to point out what's at the bottom of the screen here, and that is we have just dealt with two planes, right? The minute you start dealing with 3 planes, more planes, or higher dimensions, we're in 3-dimensional space, in 4-dimensional, 5-dimensional, more variables, well then both of these methods break down. Well, certainly the geometric one used the cross product in the last video. That only works in R3. And this algebraic method that we just did here gets a lot more complicated if we do it kind of ad hoc, the way that we just did here. So in your next unit on linear systems, you're going to generalize this method too. You're going to generalize the algebraic approach. And that will let us deal with intersections both in higher dimensions, meaning with more variables, not just x, y, z, but any number of variables, and more equations, not just 2 like we did here, but any number of equations.